everybody. Welcome back to Measure Theoretic Probability. We have been talking about convergence for sequences of random variables, and we're going to continue to do so today, but we're also going to learn about expectation or the expected value for random variables so that we can expand our convergence of random sequence repertoire. Now, I'm sure you know what the expected value of a random variable is. If you're here, I'm sure you've seen that on some level, but maybe not the measure theoretic level. So let's go. Before we go, actually, I'd like to remind you of some facts from basic analysis, possibly even calculus, convergence for sequences of real numbers. Suppose I have a sequence of real numbers, little a1, little a2, etc., and let me visualize them as some dots like this. And I'm going to draw a horizontal line here. This is not necessarily the x-axis, but something that it could appear that these dots are approaching. So maybe these ANs are converging to a number A, and this horizontal line would be at a height A. Now, if the limit as n goes to infinity of the AN is equal to A, then we know, or maybe we're learning right now, that the limit of any subsequence of these numbers A and K is also converging to A as K goes to infinity. I don't want to prove this because it's not probability or measure theory, and I'd like to get back to that, but it's pretty easy to believe. So a subsequence means you go in and you choose some values from this sequence. So you maybe poke some holes in it or pick some out. So this would be like your first value of your subsequence, your second, your third, and your fourth. I would call this AN1, AN2, AN3, and AN4. And if the whole sequence is sort of funneling down to be very, very close to A, arbitrarily close to A, then any subsequence you pick is going to be trapped in that funnel as well, and will have to converge to A. So I think that's a highly believable result that is not too hard to prove with epsilons and deltas and things like that. So we just talked about how any convergent sequence of real numbers, in that case, every subsequence you choose is going to be convergent to the same value. But my question to you now is, does any sequence of real numbers, even if they don't converge, can you find a convergent subsequence? For example, consider the sequence 0, 1, 0, 1, 0, 1, etc. This oscillating thing is not settling down or converging to any number. But if we choose A1, A3, A5, all those odd indices, we get a subsequence 0, 0, 0, 0, 0, which is converging to 0. And similarly, if we choose the even indices, we get 1, 1, 1, 1, 1, a sequence that is converging to 1. Now, this doesn't answer our question, does any sequence of reals have a convergent subsequence? But it's an example of something that's not converging to begin with that does have convergent subsequences. On the other hand, consider the sequence of reals 1, 2, 3, 4, 5 on up, just keep increasing. This is not going to have any convergent subsequence, because if you start picking values out of this sequence, your subsequence is still going to be forever increasing and just blowing up and not approaching anything. So from this, we can see that the answer to this question is no. For any sequence of reals, we do not necessarily have a convergent subsequence, unless that sequence, the original sequence, is bounded. This is the famed Bolzano-Weierstrass theorem from analysis that says that every bounded sequence of real numbers does have a convergent subsequence. Again, I want to get back to the probability, and I don't want to prove this, but here's the idea. Imagine a bunch of numbers imagine a bunch of numbers that are bounded with an upper bound and a lower bound, so they're sort of in this horizontal strip, and you can go ahead and cut that strip in half. Now, because you have an infinite sequence, at least one of those half strips have to contain an infinite number of values from the sequence. So choose the one or one of the ones that contains an infinite number of values, and take that sort of half strip that has an infinite number of values from your sequence, cut that in half. There has to be an infinite number of values either in the top or bottom or both of those littler strips made out of the half strip of the original strip. And continue that way. Keep slicing your strip in half and choosing one that contains an infinite number of values, and cut that in half and choose one that contains an infinite number of values, etc. And what you're doing is you're creating an arbitrarily narrow strip that contains an infinite number of values from the sequence. And so there is your subsequence there. You can get as close as you want to something. But now back to random variables and probability. I claim that if you have a sequence of random variables, capital X1, capital X2, etc., that are converging in probability to a random variable X, that any subsequence of those random variables is also going to converge in probability to X. So you might think this is totally obvious, or you might not. You might think it's just going to be completely analogous to the real number case. And then again, it's not real numbers, it's random variables. So let's see if we can prove this formally. I'm going to assume that we do have convergence in probability of xn to x, and I'm going to let x and k be any subsequence. Now we can assume that the indices n1, n2, n3 are ordered. We just choose things in that way. And we can assume that nk is greater than or equal to k. For example, if your sequence looks like this and you choose a subsequence by not poking any holes in this, so this is your xn1, which is x1, and this is your xn2, which happens to be x2, etc. This is the case where nk is equal to k. But as soon as you start poking holes in the sequence, then you skip something. So for this picture, xn1 is equal to x1. xn2 is actually equal to x3. So n2 is 3, and k is 2, and so you can see that your nk is strictly greater than k now, and it will always be the case once you've skipped a value. So again, you can always label things when choosing a subsequence so that your subsequence indices n1, n2, n3 are ordered and increasing, and so that nk is greater than or equal to k, and this is going to be an important convention we use in proving several things in this course, not only today, but in the future. So back to what we want to show. We want to show that x and k converges in probability to x as k goes to infinity, i.e., we want to show the limit as k goes to infinity of the probability that the distance between x and k and x is greater than some given epsilon, greater than 0. We want to show that that goes to 0. Or we can make this less than, and we can show it goes to 1, or we can make this greater than or equal to, or less than or equal to. We have some options, but I'm going to use this one. In other words, we want to show that this probability of the distance between x and k and x being greater than epsilon, we want to show that we can get that arbitrarily small. So let's choose an arbitrarily small number. Epsilon is already in use, so I'm going to use a delta. I'm going to choose a delta greater than 0. And because xn is converging in probability to x, we know that there exists a capital N, some fixed value, such that for all n greater than or equal to capital N, this probability is less than delta because this probability is going to 0. So if we look far enough, we'll get this probability within delta of 0. So these are just real numbers, and we kind of are doing the same thing that we would have done had we proven the original claim for real numbers. I'm going to plot some realizations of these numbers. I'm going to throw 0 down here. Now this picture is not correct because my little a1, a2, a3, these are probabilities and they will all be greater than 0. But I think you'll get the idea from this picture. So imagine a sequence, little a1, little a2, little a3, etc., that is converging to 0. We can take any delta greater than 0 as small as we like, and we can look within delta of 0. Again, the probabilities will never be negative, but let's just talk about a generic sequence, an going to 0. You can find a capital N such that all of the values with indices greater than or equal to capital N are within delta of 0. At least it appears so in this picture. I don't really know what's going on if I kept, plotting these points. But that's the idea behind convergence of a sequence of real numbers. We can eventually get them within delta of, in this case, 0. So to go back to the random variables, what I want to do is take k large enough so that n sub k is greater than or equal to n. Now the subsequence indices n1, n2, n3 are always increasing. Eventually they will be greater than n. And if we have that nk is greater than n, then the way we've chosen n, based on the way we've chosen n, we now have that the probability that the distance between x, nk, and x being greater than epsilon, we have that is less than delta. So if k is greater than or equal to n, then nk is certainly greater than or equal to n, and we have that the probability that the distance between x and k and x is greater than epsilon, we have that that probability is less than delta for every k greater than or equal to n. I'm just trying to not work with these indices n1, n2, n3, but a sequence indexed by 1, 2, 3, which is the index for the subsequence. Because our delta was arbitrarily chosen to be something greater than 0, we can choose delta as small as we want, and this means that the limit as k goes to infinity of the probability of the distance between x and k and x being greater than epsilon, this is going to 0. This is how you show that x and k converges in probability to x, so we're done with the claim. If you have a sequence of random variables xn converging in probability to a random variable x, then any subsequence you choose will also be converging in probability. If the indices on the indices are bothering you, when you get to this point, you can redefine xnk to be yk. So xn1 could be some y1, xn2 could be some y2, and then you can be working with individual subscripts again and not subscripts. If that helps you, if you had any problem believing this final line here. I also claim that if the random variables xn are converging almost surely to x, the stronger form of convergence that we have, then any subsequence is also converging almost surely to x. This proof I'm going to leave to you. It is kind of similar. It's a different type of convergence, but it's fairly straightforward. You can kind of follow the proof points in the previous proof and adjust things for almost sure convergence. Let me know if you want to see the proof. Let me know in the comments below, and I can always post that as well, but I think I'm going to skip it here. I think neither of these results are too surprising. Convergence in probability or almost sure convergence will imply convergence in probability or almost surely for subsequences. Let's talk now about something that might be surprising to you. You'll recall that almost sure convergence is a stronger form of convergence. That is, if xn converges almost surely to x, then we have convergence in probability, whereas if xn converges in probability to x, we may not have almost sure convergence. Here is my claim for you now. I'm going to call it a theorem. If xn is converging in probability to x, our weaker form of convergence, there exists a subsequence that is converging in the stronger sense to x. There exists a subsequence xnk that is converging as k goes to infinity to x almost surely. So this one is actually kind of an interesting result, that we can start with a weaker form of convergence for sequences of random variables and look in there and find a subsequence that converges in the stronger sense. Let's prove it. We are, of course, assuming that the xn converge in probability to x. This means that for k equals 1, 2, 3 on up, the limit of the probability of the distance between xn and x being greater than 1 over k must be 0. What I'm doing here are choosing a sequence of particular epsilons, and this limit has to approach 0 no matter what epsilon I put here. So this is like epsilon 1 is 1, epsilon 2 is 1/2, epsilon 3 is 1/3. It's just a sequence of epsilons, and convergence in probability gives you a statement that has to hold for all epsilons. So we have this result here. Note that for each k, because this limit is going to 0, for each k, we can choose n large enough to get this probability arbitrarily small. I'm not going to be arbitrarily small here. I want to get this probability to be less than 1 over 2 to the k. So fix k. For any 1k, this limit is 0, which means we can get it arbitrarily small. This means we can get a large enough n so that this probability gets smaller than, in particular, 1 over 2 to the k. So we can do this for every k. So I'm going to do it for k equals 1 and choose an n, for k equals 2 and choose an n, etc. That'll get me something I'm going to call n1, n2, n3. In other words, I'm going to label these n's as n1, n2, n3, and nk to be the one that goes with the generic k. We can also choose this n1, n2, etc. so that they are ordered. Say you've already chosen your n1 and you're trying to choose your n2. your n2 has to be large enough so that you're getting close enough to 0. And so if your n2 is actually less than n1, you can look further. You can start looking at the sequence from n1 on up. Why do we do this? Let's consider the sum of these probabilities. The sum as k goes from 1 to infinity of this probability we now know is less than or equal to the sum as k goes from 1 to infinity of 1 over 2 to the k. This is, of course, 1/2 to the k, and this is a nice geometric sum that's going to equal 1/2 over 1 minus 1/2, which is going to equal 1, which is finite. I'm going to ask you to recall a fact from the previous video where I had 4 properties that were labeled 1, 2, 3, and 4. This was property 4, where we showed that a sufficient condition for almost sure convergence of xn to x is that the sum as n goes from 1 to infinity of the probability of the distance between xn and x being greater than 1 over n. If this sum is finite, that was enough to say we had almost sure convergence. Does this really look like this? If you are worried, again, you could relabel xn1 to be a new random variable y1, xn2 to be a new random variable y2, and so then this xnk would be replaced with yk, and it would look much more like this. But either way, we have the result now that the xnk's are converging almost surely to x by this property 4 from the last video, and this is the subsequence of the original sequence of random variables that converge in probability to x. We have exhibited a subsequence that is converging in the stronger, almost sure sense to x. That was pretty fun, but I have another theorem for you that may be even better. So if you have a sequence of random variables xn converging in probability to x, that happens if and only if for each subsequence of this sequence, xnk, each subsequence has to contain a further subsequence that converges almost surely to x. These are not facts that you may care about standing alone like this, but these theorems are going to be things we use to prove other things later in the course that we actually care about. So let's prove this. One direction is already done, and that is the forward direction. If we assume that xn is converging in probability to x, then we have seen earlier in a claim that that means that any subsequence xnk is also converging in probability to x. And now by the previous theorem, that subsequence has itself a subsequence that is converging almost surely to x. So we're done with this forward direction. It's the other direction that's going to be a little more interesting to prove. I'm going to start by assuming that this part is true, that each subsequence xnk contains a further subsequence that converges almost surely to x. So I've got a sequence of random variables x1, x2, x3, and then for every subsequence, I can go in there and find a subsequence of that converges almost surely to x. I claim that that's enough to establish convergence in probability of the original sequence. I'm going to do this by contradiction. I'm going to suppose that the xn's do not converge in probability to x. This means that, our for all epsilon statement is going to fail. This means that there exists some epsilon greater than 0 for which this limit is non-zero. If this limit is non-zero, then this probability is bounded away from 0. So this means that there exists a delta greater than 0 for which infinitely many of the xn's are such that the probability that the distance between xn and x is greater than epsilon is greater than delta. We can't get down to 0. We're being sort of bounded away from 0. And this probability cannot get smaller than this delta that we've chosen. There's going to be an existing delta for which this holds. Okay, so look at that collection of the infinitely many of the xn that satisfy this. Choose any subsequence from that collection. So this subsequence of random variables has been chosen from the collection of random variables that satisfy this, and therefore this is satisfied. I have a sequence xn, I have a subsequence, and by the assumption of the reverse direction of this theorem, there is a subsequence to that subsequence that must converge almost surely to x. This was our assumption in this direction of the proof. Again, the x n k j, if you will, another subscript. So we're looking at our xn1, xn2, xn3, and we're choosing just selected values out of that. and we're calling the new indices xn, k1, xn, k2, etc. These are converging almost surely to x, and because almost sure convergence is stronger than convergence in probability, this implies that the xn, kj is converging in probability to x. If these subscripts are too confusing, you really can say this in English language, and you can say, I have a subsequence and a subsequence and a sub-subsequence, and this must be converging. And you really don't have to label these like this, if that helps you. But if we have convergence in probability of these guys to x, that means that the limit as j goes to infinity of the probability that the distance between x, n, k, j, and x greater than epsilon, this probability has to be going to 0. But the subsequence was chosen out of random variables for which this probability was bounded away from 0. So this probability can't be going to 0 with this subsequence, and we have a contradiction which arose from our assumption that we did not have convergence in probability here. So we have proven our statement. Xn converges in probability to x if and only if every subsequence of xn, call it xnk, if every subsequence contains a further subsequence that converges almost surely to x, then we do have convergence in probability for the original sequence. So we had two claims that I don't know if they're obvious, but probably felt pretty good to you, that if you have convergence in probability, then any subsequence converges in probability, or if you have convergence almost surely, then any subsequence converges almost surely. Then we had two more interesting theorems. If you have convergence in probability, you have a subsequence that converges almost surely, and this one that I just stated, which I find really hard to say, so I'm not going to attempt to say it again. I want to take a break from convergence to talk about expectation or expected value for random variables. Again, the point is to really move to our next type of convergence for sequences, but for the rest of today, I'm not going to talk convergence at all. I'm sure you recall expectation or expected value to be a probability weighted average. In particular, for a discrete random variable x, we usually write like a capital E for expectation, and then parentheses. I like square brackets. Some people don't put anything there. Not really people in probability and statistics, but people in physics, maybe. I don't know. People have different notations, but this is the notation I'm going to use. Is defined to be the sum of each x times the probability that x equals x, and we're going to sum over all possible x, and I purposely write it like this and not like a sum as x goes from 1 to infinity, because just because we're talking about a discrete random variable does not mean we're talking about integer valued random variables. So this x will run over all possible values for the random variable, or even more, because if it hits on values that the random variable cannot take on, the associated probability will be 0. So hopefully this is a definition of expectation that you've seen before. Now let's look at it from a measure theoretic point of view. In today's video, we're going to start off with and stick to simple random variables only. So assume you have a probability space, an omega, a curly f, and a p, and you have a random variable x that is a measurable function from omega into r. X is a simple random variable if it takes on this form. If x of omega can be written as a sum as I goes from 1 to n of some constants xi times an indicator that says that omega is in the set ai. This is old stuff for us. Once you have a random variable written this way, we define the expected value or expectation of this random variable to be the sum as I goes from 1 to n of x sub I times the probability measure of the set a sub I. For this to make any sense, and for this to make any sense up here, for this to be a measurable function, recall that we do need the sets, capital A1 through capital AN, to be measurable sets. In other words, we need them to be in curly f so that this probability of AI makes sense over here. This is the definition of a simple random variable, but a random variable that can be represented this way might have another representation, may have multiple representations of this form. And I want to spend the rest of today's video just quickly trying to convince you that that's not going to affect the expectation. When I see a random variable in this form, I generally think that we are using what I call the canonical partition for this random variable. That's not terminology that's used out there. That's just my own terminology. So you're probably not going to find it if you're looking for it. But I assume that the little x1 through little xn are distinct, right? So if you take an omega in capital A1 and it maps to the number 3, and you take an omega in capital A2 and it maps to the number 3, then why don't you just define A1 to be A1 union A2 and have that single set mapping to the number 3? So we can assume that the little x's are distinct, and we can assume that the capital AIs are exactly what they need to be. In other words, the inverse images of those singleton points. This is my definition of the canonical partition for a random variable. To visualize it with n equals 4, suppose we have omega that looks like this, and we've partitioned it into, in this case, 4 sets, A1, A2, A3, and A4. And in general, they do not need to be contiguous like this. The A1 could be made up of several pieces, but we're going to take each point in this omega and map it onto the real line. Every point that comes out of this set, capital A1 over here, is going to map to this little x1 over here. Everything that comes out of capital A2 over here is going to map to little x2 over here, etc. This is what I call the canonical partition. If we use this and recall our new definition of the expected value of x being the sum as I goes from 1 to n of little xi times the probability of ai, note that the probability that the outcome of your experiment is in ai, that's how the random variable x takes the value little xi. So the probability that x takes the value little xi just sort of backtracks to the probability that the outcome of your experiment was in capital AI. In other words, this probability of AI is equal to the probability that x equals xi, and this, as usual, is shorthand notation for the probability measure of the set of omegas for which x of omega is equal to little xi. This is our usual definition of expectation, and this is our new one, so we can see that we're not really doing anything different or crazy here. So I did say that the definition of expectation will be well defined and still hold, even if you represent the same random variable with different partitions, and even using sets that are not partitions of omega, that do not partition omega. So we need to be mapping everything in omega somewhere. So we need these sets, capital A1 through capital AN, to sort of cover the omega. We need their union to be the full omega, but they do not actually need to be disjoint, as you'll see in a few moments. Suppose that we have a random variable x with this n equals 4 example and the canonical partition, and suppose that it can also be represented as a sum as j goes from 1 to m of some constant yj times the indicator that omega is in a set bj. I'm going to assume that these bj's form a partition right now, and note that we just can't take any partition. Suppose I took m equals 3 and my capital B1 through capital B3 looked like this. This is going to force some things to happen. Let's pick an omega from omega. Suppose we pick this point right here, which if we look at it through the different partition is right here. If this omega is up here, then according to this representation of x, when you plug it in, you'll get little x1 as the value for x. But this little omega being right here, according to this representation for x, when you plug it in for omega, you'll get little y1. And both of these are supposed to be representing the same function x of omega, so this forces little x1 to equal little y1. I'm going to now take another omega, say over here. According to this representation, because my little omega is in capital A2, it is going to map under the x function to little x2. But according to this partition, it is going to map under the x function to y1 again, because this omega is still in B1, just like the first omega. So we have that x1 equals y1, and x2 has to equal y1. And this means that x1 has to equal x2, and this contradicts that the a's were the canonical partition where we had distinct xi's. So the point I'm trying to make here is if your random variable can be represented, if your simple random variable can be represented in two ways, there's a lot of built-in stuff that is forced to hold before you even start to think about expectations. And that built-in stuff that is forced to hold is going to force the expectations to be the same. In general, when you have a random variable represented according to two different partitions, whether one is canonical or not, we must have that this little xi is equal to little yj if and only if the set ai intersected with the set bj is non-empty. That's what we basically just saw in our 4-point, 3-point example. Okay, I am going a little longer than I meant to go. So I am trying to get to the point that no matter what partition you use to define x, and we may actually use sets in that simple random variable definition that are overlapping. Our definition of a simple random variable did not assume we were using a partition, but we can always think about it that way if we rewrite things nicely. No matter how you represent x in terms of a simple random variable with sets ai and bi and maybe another group of sets ci, I claim the expectation is going to be the same no matter which representation you use. So that's what I'm going to come back and prove next time on Measure Theoretic Probability. I hope to see you there.